So for this, it's pretty easy, right? Do power rule and you get it back. I'm not going to do it, but what we'd be looking for is for it to become this, right? Okay, so let's compare that to part B. For part B, that's a problem I like to put on a test. Only because if you mess up B, then there's some like major foundational problems. Like we need to sit down, talk. And so it's kind of a red flag problem for me. 2x plus root x minus 4 plus x cubed all over cube root of x. Now that looks pretty bad. Here's what I don't want you to do, all right? This is the mistake, is that people will look at this and go, okay, these are separated by addition and subtraction. I can do this one by itself, this one by itself, this one by itself, this one by itself. That's okay. And then they come down here and say, oh, that's just the power of x. I do that by itself. So my answer is just the antiderivative of this up here, and then divided by the antiderivative of this on the bottom, and then I'm done. That's not correct. What you're doing there by doing that is you're actually undoing a quotient by assuming that the antiderivative of a quotient is just the antiderivative of top and bottom separately. And you're not allowed to. So your only hope here is to try and get this to not be a fraction anymore. And can you do that?
Yes.
Yes. Because you have a single denominator, right? You can separate it into 4 different fractions, right? This is the same as 2x over cube root of x plus root x over cube root of x minus 4 over cube root of x plus x cubed over cube root of x, right? That you're allowed to do. Right, Kyle? Yeah? Okay. And then, what can you do? You can start doing power rule, yes, as soon as we get a single power of x, though, right? Like this has to be put together to become x to a power. So let's just talk about that. This is college algebra. X to the first power over x to what power? 1/3, right? Cube root is 1/3. And when you have this, you subtract. 1 minus 1/3 is 2/3, right? Nope. It's 1. Yeah, this is going to be 3 over 3 over 1. Okay, everyone good? Yeah? Okay. Everyone okay with that?
And then 2 would just come along, right?
Yeah, the 2 will come out. So let me rewrite it. I haven't done any antiderivative yet. This is just rewriting the problem, right? That's just rewritten, right? How about this one right here? I have to come over here on the side. I have to do some college algebra again. That's, I'll do it over here. This is x to the 1/2 over x to the 1/3. This is x to the 1/2 minus 1/3. 1/6. 1/6. Common denominator, put it together. So plus x to the 1/6. So minus 4, that's what's here, right? Minus 4. This is x to the 1/3 in the denominator. I bring it up, x to the negative 1/3. Do not forget to bring that up. So I'm looking at this right here. It was 4 over x to the 1/3. I cannot use power rule on this because the 1/3's in the denominator, or the x to the 1/3 is in the denominator. I have to bring it up to become x to the negative 1/3. Do y'all see that?
Yes.
Okay. I still haven't done any calculus. Do y'all agree? Nothing I've done yet is calculus. Everything I've done is algebra up to this point. And the last one, what am I going to be doing? I'm going to do x to the third, right, over x to the 1/3. And that's 8/3. So Alex, you keep on giving me these answers. I'm just going to ask you, how are you doing 3 minus a third so quickly?
Just find the common denominator.
So mentally,
Yeah.
you're doing 3 over 1 minus 1 over 3, like in your head, kind of?
Kind of, sort of, but I just at the top of my head recognize that if you put it as, yeah, if it's 3 over 1, yeah, if you do it that way, you do it, but I don't do that one with my head. I just assume that it's 9.
So you just kind of are automatically seeing that 3 is 9/3.
Right.
And then once you're there, it's subtraction, it's just
Right.
the numerators. Okay. So that's stuff, I mean, it's just everyone's at different places when it comes to like adding and subtracting fractions. You actually want to be right there. Where you are, Alex, is perfect. That's where you want to be. It's going to take time to develop that. You have to work with enough of these to get quick with it. But at the end of it, you just have to have your own way of doing it, all right? You don't want to be breaking out your calculator to do 3 minus 1/3, okay? That has to, you can't have an approximate answer. It has to be a fraction. So what is this? Plus x to the 8/3. Okay. Now we do antiderivative. So look at these ends, right? These are some weird ends. 2/3 is one of the ends. 1/6, negative 1/3, 8/3. You do this, okay? I want to give you a few minutes to see if you can come up with these on your own, all right? And write down. And what I'll do is I'll call some names, some people I've never met before. I'm going to call on you. I'll call on 1, 2, 3, 4, potentially 5 people. Passing the sign-in sheet around. If anyone has a question about something, you can raise your hand. I don't mind coming by and helping out. The top one first, like.
The exponent power, and then flip it. Take those.
You mean like add 1 to this?
Yeah, and then
Just figure out what that is and then flip it and put it in front? Yes. You can do that. Are we ready? Y'all ready? Okay, I'll give somebody an opportunity to volunteer, but it's got to be someone I haven't really interacted with. So, let's see. Does anyone want to volunteer? Kristen? I don't know much about Kristen? Kirsten, sorry. Kirsten. Do you have the first one?
Yeah.
Okay, what do you got?
6 over 5 x to the 5 thirds.
6 fifths x to the 5 thirds. Agree? Yes? So you had out here, what? So this was 5 thirds, and this became 3 fifths out there. That's correct. Who else? Is it Michael? Michael? Did you get the second one yet, Michael?
6 over 7
6 sevenths.
x to the 7
Is that right?
Yes.
Yes? Okay, good. And then no one's volunteering for this one? Go ahead. You can go, James. 6x to the 2 thirds is what you got for this one? So this was 2 thirds out here, and this was 3 halves out front, like that? So no one's disagreeing? I guess we all agree it's correct? Okay.
As long as you keep the minus.
Yeah, there's a minus here, right. Okay, so minus, this was plus 6 sevenths, x to the 7 sixths. And, okay, so everything else looks good there? And then the last one, 3 elevenths, x to the 11 thirds, then plus c? Okay, so we're all good? We all agree? Okay. Looks good then, I guess. I'll trust you.
Checking your answer with that, wouldn't that be kind of a pain?
I don't know, let's just check the first one, okay? If you were to do this to this, right, you multiply 5 thirds, 6 times 5 thirds, right? 30 over 15, that's 2, right? So that's this. And then you subtract 1 from this, so you subtract 3 thirds, and you get 2 thirds. So yeah, it works. So tedious, not too bad. Okay, let's look at the next example, C. What example C is checking is that you remember those common antiderivatives that you should know from Cal 1. So these are not power rule, right? This is not x to a power. This is, trig functions. What's the antiderivative of sine? Antiderivative of sine. Negative cosine. And so that's the one you got to be careful with, right? And you can always check yourself, right? What's the derivative of cosine x? Negative sine x. That's why you have to have a negative in front to make it a positive. And then the antiderivative of secant x tangent x. Just secant x. So derivative of secant x is secant x tangent x, so plus c. So those are ones that need to come from recognition, all right? And let's look at D. 2 plus x squared over 1 plus x squared. What do you think? Can you just do top and bottom separately? No. So your only hope that so far from what we've learned is that you can either break this up into powers of x, with pluses and minuses between them, or it's something that you recognize from the table, from derivatives from Cal 1. Can you split it like we did the previous problem?
Yes.
The one where we did the different ones and then write each one as a power? Couldn't you? Can you?
Yes.
Like 2 over 1 plus x squared over 1 plus x squared?
Right.
How can you split that? You got to be careful the way you split this.
2
Oh, yeah.
plus 2 over 1 plus x squared. That's the denominator, then plus x squared.
Plus x squared.
This you can do. That you are allowed to do.
Isn't that sine of that? So, oh, you had the limit. Never mind.
Well, that you could do. Do y'all agree I can do that algebraically? But does that help? Not really. All right? Not really.
So would we break up the first, yeah, the first part into 1 over x, 1 plus x squared plus 1.
I think I know what you're saying, and that's super clever.
So that would be 2 inverse tangent.
Yeah, okay, so watch this. Now, I don't know. I don't know if this is what you're saying, but I think this is what you're saying. In the very beginning of the problem, could you do this? I think we're going to get to the same place. Could I have done that? 2 is 1 plus 1? Am I allowed to split this right here? Like do 1 over this and then this over this? Yeah? So that would become 1 over x plus, 1 plus x squared. That's 1 over this. And then what's this over this? So plus 1?
So it would be tangent inverse x plus 1.
That's right. Well, plus something. So we've just done some algebra here, right? To split this up? Yes? Ooh, that's kind of strange, isn't it? How do you see that, James?
I just looked at
Okay. Yeah. So you just recognize it. Okay, so again, there's no way I teach that. I can show it to you, right? But I can't teach you to see that. And that becomes a theme in this class. Seeing things, recognizing patterns. Now this is kind of unorthodox, but it works, doesn't it? Now let me show you another way you could have gotten to this, all right? If you didn't see that, you could have done this. Remember that? College algebra, long division. Right? So how do you do this? It's that divided by this, right? So what do you multiply x squared by to get x squared? 1. Then you do multiplication here, here. You come through and subtract, so it changes the signs, right? And when you add down now, you get nothing, and here you get what? 1. X squared doesn't go into 1, right? So you get plus your remainder over your divisor. The remainder over this, that's this, right? So you could have got to the same result with just long division. Now, we have not done the antiderivative, have we? Just rewritten the problem. And now for the antiderivative, you have to be able to recognize these. And this is the antiderivative, this is the derivative of what function? The derivative of arctangent. So do you remember when we studied arctangent just a couple of first class? I told you that the derivative of the inverse tangent of x was 1 over 1 plus x squared, didn't I? And I told you to put a star next to it because we're going to use it a lot. Do you remember that from the first class? Well, that's why. Look, what's the antiderivative of this? Arctangent of x. We recognize that. Okay? And then what is the antiderivative of 1? Now be careful with this. X. X. Now we hadn't done this yet, had we? I hadn't done that before. The antiderivative of 1 is x because the derivative of x is 1, right? What do I still need? Plus c. Does anyone have a question about this? Because we're done with this problem. Yes?
How did you get the 1 over 1 plus x squared plus 1 there?
From
Splitting up the 2 and
Okay.
plus 1?
So I split this into 2 fractions. I do this piece over this.
1 over 1 plus x squared.
That's this. And then I could have done individually, but I decided to clump these together and put that over this. And that gave me the 1. still have about 10 minutes. All right, so we're going to talk about rectilinear motion. Rectilinear motion. Objects that are moving in a straight line, basically, is what we're talking about. And in Cal 1, I hope that you were shown that if you have an object moving in a straight line, okay, so some object moving in a straight line, usually we'll look at this as like two-dimensional or one-dimensional, where it's just like a car going down a track or something like that. Then if you have a way of measuring time and position of the object, right, that the first derivative represented the velocity and the second derivative represented the acceleration. Well, if we're now talking antiderivatives, there must be some way that we can go from an acceleration backwards to a velocity and from a velocity backwards to a position. And that's what this is about. So look, it says, recall that if the position of an object moving in a straight line is given by some function s of t, so this is the function s of t, that the velocity, right, v of t, the velocity of this object is the first derivative, and the acceleration is the second derivative. Therefore, if somebody gives us an acceleration function, right, if somebody gives this to us, and I want to know what velocity is, will I be able to get it? Yes, but there will be kind of a sacrifice I make. When I find the antiderivative to go backwards, am I going to be able to get the exact function? I'm only going to be able to get a family of functions, right? Understand? And that's not exactly perfect, the exact function we're looking for. But it gives you some idea of what it should look like, right? It's within a family. And then if I have some idea of this function, I should be able to go back and get this one, right? The position. I would have to do the antiderivative velocity. And again, I will have there's a give and a take. I'll be able to get it, but it'll be a family that I'll be looking at. Yes? All right, so here's an example. We have an acceleration function that's given to us. Acceleration of an object is 24t minus 6. And you're given some other information. S of 1 equals 7, and V of 2 equals 41. Find the position function, and then find S of 2. So I'll draw a quick picture of what's happening here. I'm going to draw it backwards. Here's the acceleration function. Do we have this function? Yes? It's 24t minus 6, right? It looks like this. If I were to graph it, it has a y-intercept of negative 6, has a slope of 24. It's like this. This is our it's a line, isn't it? It's a line? Okay. And I think any t values, no negative t values, because it's probably time, right? So it's just this light right here. Okay. Now, I'm going to try and go backwards from that to get the velocity function. And we know that when we go backwards to get this, it's going to be a whole family of functions, right? And they're actually going to be a bunch of parabolas, aren't they? Because this is a linear function. Antiderivative should take us back to parabolas. So it's all these parabolas in here, right? But they gave us something else. They told us the velocity at 2 is 41. What does that do for us? At 2, I'm at 41. That point must be on my graph, right? That's actually going to fix, instead of having a whole family of parabolas, that nails down the one parabola it can be. That's all I need. Just one point on that curve, and I can tell you exactly which of those parabolas it is. So that's an important piece of information to know. This right here, these things, in problems like these, are known as initial conditions. Now, it's bad wording in this problem because initial usually makes you think starting, like the initial. It's most of the time it's like S of 0, V of 0. It's the start at the very beginning, at time equals 0, it's the condition you have. In this case, it's not really an initial condition that we have. I'm telling you that at 2 seconds, the velocity is 41, and at 1 second, its position, right, S is position, the position is 7. Do you see why initial isn't really a good word for this? All right. And then going backwards from here, see, once I nail down that specific parabola, I can go back to the position function, which is going to be a cubic function, isn't it? If this one's a parabola, this one should be a third-degree polynomial. And there's a family of them. But again, I've got some information. At 1, I'm at 7. And that's going to nail down the exact position function. Once I have the exact position function, then I can answer parts A and B. All right, so let's see how to do this. I have 5 minutes. Hopefully we'll have enough time. Here we go. The velocity function should be the antiderivative of this. What is the antiderivative of 24t minus 6? So 24 times 1/2 t squared, right? And then minus 6t.
Yes.
Be careful with these constants, right? In Cal 1, we were like derivative constant 0, derivative constant 0. But in Cal 2, the antiderivative of a constant, the variable just appears, doesn't it? That's what happens. And then plus c. So the velocity at time t is 12t squared minus 6t plus c. Yes? Now I'm going to use the condition, okay? The condition, I'm going to say here, but v of 2 was 41, right? That implies that when I plug 2 into this for t, it should spit out 41. So when I plug in 2 for t, I should get 41 out, right? So this is, so what's this? 48 minus 12, right, which is 36, plus c equals 41. So c is 5. So c is 5. So look at our train of thought here is this. We know the acceleration. We go backwards to get the velocity. I know the velocity. I know it's a family of curves. I don't know which one it is. I use the condition that allows me to figure out what that c is. And now I know exactly what that function is. The velocity function is exactly 12t squared minus 6t plus 5. Yeah? Okay. Same principle. We're going to go back and we're going to get position now. So we have to take the antiderivative again. So for the position, s of t, we find the antiderivative of this, which will be 4t cubed minus 3t squared plus 5t plus c. Now it's okay to use c again if you want, because we already found what that c was, right? But just so there's no confusion, I'm going to use capital D instead. But what do we know about this? But s of 1 is 7, which implies that when I plug 1 into this, I should get 7 out. So 4 and then 1 cubed minus 3 times 1 squared plus 5 times 1 plus d equals 7. What is it? D is what? 1? Yeah? I'm not doing the math in my head, so I'm trusting you. Yes?
Yes.
D is 1. Okay, so that means D is 1?
Yeah.
And that is your position function. That answers part A, doesn't it? That's part A of the problem. What is the position function? And then the last thing, S of 2. So just plug 2 into that and you get an answer. So you can't find S of 2 if you don't know what S is, right? Okay, I have 30 seconds. I probably don't have 30 seconds, but I want to show you something real fast. Does anybody know on Earth what the acceleration of gravity is? Negative 9.8 meters per second squared. Does anyone know what that is in approximately feet per second? About 32. 32 point. You've heard this before, something like this, negative 32 feet per second squared, depending on what units you want to be in. Okay. Yeah. Well, let's assume Earth, and let's assume that we're averaging out. You know, of course, it's different if you're further away, right? So let's just assume that. So on Earth, all objects, if you just let them go, have an acceleration of negative 32 feet per second, right? If you go backwards and find the velocity, the antiderivative of that would be negative 32t, right? Plus some constant that I don't know. But I want you to pay attention to something. At v equals 0, what would I get? If I plug in 0 into this, what would I get? C, right? Wouldn't that be the velocity at the beginning? Right? At time 0, isn't c the velocity at the beginning? Yes? So let's somehow let you know that that c will always be the velocity at the beginning. What I'll do is I'll write this instead. Instead of calling it c, call it v sub 0, initial velocity. So I know the acceleration on Earth. I know what the velocity of the object would be, but you would have to tell me what the initial velocity of the object was. Now, let's go backwards again. What's s of t? What's the antiderivative of this? Negative 16t squared. What's the antiderivative of a constant? So what's the antiderivative of 4? 4t. So what's the antiderivative of v naught? V naught t. But then I have to say plus another constant, right? Let's call it d. Now I want you to notice something about d. If I let s of 0, right, that would be at time 0, it would kill these two off, and I would just have this, which would be the initial position, wouldn't it? The starting height of the object. So I'm going to, instead of calling it d, I'm going to call it s sub 0. Have any of you ever seen that formula before? Physics? But, yeah? Yeah, okay, so I don't know, maybe in high school or something. This is in college algebra. I use this as an example. This is any object on Earth. If you let it go, its position is given by this formula. The only two things you need are its starting velocity. So whether or not, if you just drop it, the velocity is 0. If you throw it up, the velocity is positive. If you throw it down, the velocity is negative. So if you just let it go, that's 0. And then this is just how high off the ground it is. This formula did not fall out of the sky. It actually comes from the fact that we just were able to measure the acceleration. Once we knew acceleration, we just went backwards. Pretty amazing. Anyway, have a good day. Do your homework, which is what? Right there. 1 through 33, odd, 39 and 41 on page 252. Keep up with your homework. Things are going to start getting real interesting soon. If they're, yeah, you can throw those away or just put them on my desk.